So it seems kind of strange to say it, but we're actually almost done with all the concepts for Chapter 23. There's only two more just really little ones I want to talk about. So first one is this. Let's go back to gravitational potential energy. I know I told you I was done talking about that, but I do want to talk about one other thing. Let's look at, we've got this cliff here. We've got a ball here. We're going to roll it off this diving board, and it's going to go down to there. All right, so what do we know about this? Do we know what the potential energy is here? Well, we can make it up, right? We don't really know, but we do know it has some potential energy here. And we can define our zero to be wherever we want it to be. But the one thing that we do know is that the potential energy here is higher than the potential energy here, right? We all agree with that, right? Here's where electric potential differs, because what is the electric, remember the electric potential is this, once again I'm writing it in terms of V, delta V, that is the electric potential energy per charge. All right, what's the key here? The key is that if you put a blue rock here, and that blue rock went, would it have a higher or lower potential energy here than here? Higher. What if you put a red rock up here? You put a red rock up here, does it have a higher potential energy or a lower potential energy from here to here? Well, it's a higher potential energy here than it is there. This is where things are different for the electric potential energy, because the electric potential is per charge, but the electric potential energy difference, if I have this electric potential difference, I have this electric potential difference. I'm sorry, I misspoke. If I have this electric potential difference, I have this electric potential energy difference. So, is every Q the same? No. Some are positive and some are negative. So, is it possible that I could have one charge that has higher potential energy in one spot and lower potential energy in another, and then I have a different charge where I have a lower potential energy, a higher potential energy in the spot where the other one has the lower potential energy, and a lower potential energy in the spot where the other one has the higher potential energy? And of course, you know now the answer is yes. Okay, so that's the first important thing to know. There's one more thing you need to know, and then really, like I said, you're done. Everything else is just specific applications of this. Kind of like the Gauss's law chapter, where Gauss's law is pretty simple, and it's just, all right, how are we going to apply this thing? Same thing is generally true here. But there is one more thing we need to know. What we know is minus E dot dl equals delta V. Okay, yeah, I'll just leave it at that. Okay, you guys understand this is from A to B, and this is VB minus VA, blah, 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 blah. But it doesn't matter right now. This is the important point. The important point is, what is this? How are we making this E? Is there anything in this expression that constrains how we made E? No. And we already know what happens, how we can make E different ways. And this is what I mean. We could make E from one charge. We could make E from 2 charges. We could make E from 8 charges. We could make E from a ring of charge. We would make an E from an infinite plane of charge. So whatever this E is, it could be that this is E1 plus E2 plus E3 plus blah, blah, blah. However many E's you want, it could all be that dot dl, right? And because this is just a simple dot product, what this really means is minus E1 dot dl plus, minus E2 dot dl, and et cetera, et cetera, et cetera. Okay, so our delta V is just going to equal the sum of all these individual things. Well, when I look at this right here, whatever has made E1, this is just something, what is this expression? I'm not sure if this is showing up, so I'm going to tilt this up. This expression, E dot dl, I'm going to put that 1 down there. This is just delta V1. Well, what does that mean about when I have all of these separate ones here? What it means is that this, the same principle of superposition we used here for the electric field also applies for the voltage. So if I can calculate the voltage for one of these, then I can to get the voltage for like 8 charges, for example, I would calculate the voltage for one charge, then calculate the voltage for another and another and another. Now, the one difference is this. Because we're only looking at this delta V, we need to be certain that when we do this, we need to be certain that we're measuring them all from the same spot, okay? That we're measuring them all from relative to infinity, for example, and that's going to be a really common one, is that we're just going to measure it relative to infinity. Not always. I can't remember if any of the problems I gave you require a different assumption, but it doesn't matter. But the point is this. The same way you did superposition with the electric field, you can do superposition with the electric potential. And that's it. You now know everything you need to know to do all the problems in Chapter 23 and to read the rest of it and follow everything from there as well. However, what I will do now is I'm just going to go ahead and do some example problems after this. And so we're just going to look at different specific situations so you'll understand kind of how to apply all these things we talked about. Stop.